Hi everyone, welcome back to my channel. Let's see what I've studied over the week. The topics include what does synchronization do apart from locking? Second, what are volatile variables? Third, what is thread confinement? So let's get started. Here we can see class report system. Report system has two variables, report ID and report ready. Thread 1 is preparing the report and thread 2 is printing the report. While preparing the report, thread 1 is writing report ID to 101 and converting report ready to true. Then thread 2 is checking if report ready is true and then it is printing the report ID. Now let's see what can go wrong with this code. Here, report ID and report ready are being shared between two threads, thread 1 and thread 2. So they are shared mutable variables. Shared mutable variables should always be accessed in a thread-safe manner, which is not done here. So the first thing that can go wrong in this code is that thread 1 and thread 2 can access these both variables at the same time, leading to race conditions which can lead to inconsistent or unpredictable outputs. So this is a very common scenario, obvious scenario. Let's see what else can go wrong in this. Now let's see the code in prepare report. We are assuming that when report ready is set to true, the report ID will be 101. And that's the check we have written in thread 2 print report. If report ready is true, the report ID will be 101. This assumption is completely correct for a single threaded system and this code will work over there. But in multi-threaded systems, more things come into picture and this code doesn't work. Now let's see why. JVM, compiler, and runtime do some reordering with our code to give us performance benefits. That means report ready can be set to true even before report ID is set to 101. That will completely invalidate the condition which thread 2 is checking. So then why does this code work in single-threaded environment but not in multi-threaded one? That is because this reordering is not visible to the executing thread. The reordering is done in such a way that the core logic of the executing thread is not affected. But when multiple threads start working together, the reordering within each one of them is visible to each other. So that is why this code will fail with unpredictable output in a multi-threaded system. Now let's see what is the final problem. The actions done by thread 1 in prepare report, that is setting report ID and report ready, are not guaranteed to be visible to thread 2 immediately or even at all. Thread 2, there is a possibility that thread 2 will still be seeing stale values for report ready and report ID or for either of them. That can lead to unpredictable output. Now let's summarize the problems we faced when the code is not synchronized. First is race condition. Second is reordering. And third is no visibility. Synchronization helps us with all these three problems. Synchronization provides us with atomicity, that is converting compound actions to atomic actions to avoid race conditions. Second, it makes the actions done by thread A after entering the synchronized block visible to other threads that are entering synchronized block after it. It also prevents reordering of code inside the synchronized block. So the techniques used to achieve synchronization are: first, use synchronized methods while accessing shared mutable variables. Second, use locks, but use the same lock every time for a particular variables or set of variables that are participating in any evaluating condition, or you can say invariant. So while using locks, this note should be kept in mind. And third is use volatile variables. We'll come to it in the next section. Now let's move on to the second section, that is volatile variables. As we have already seen, without synchronization, there is no guarantee that the actions performed by one thread are going to be visible to other threads. So volatile variables help us with that. They give us the most recent write to that variable. So they help us with visibility. They also don't participate in reordering with non-volatile operations around it. That means the code that is going to be executed before the volatile variable is guaranteed to be executed before it. Though they don't participate in the reordering. So what does a volatile variable not do? It helps us with visibility, it helps us with the reordering issue, but it doesn't do locking. So it is helpful in visibility and reordering, but not locking. Let's delve more into the visibility aspect. Visibility of a volatile variable is not limited to the variable itself. The variable acts like a gate. Everything executed by thread A before volatile variable is visible to thread B after reading that volatile variable. Let's look at this with an example. Thread A is setting x to 10, y to 20, and then it sets volatile variable ready to true. So everything that is executed before the ready is visible to thread B after it reads ready. So when thread B reads ready and then moves in the block, x and y are guaranteed to be 10 and 20. Now let's see some other case. Here we see thread A is setting data to 42 and then it sets volatile variable ready to true. So everything before this volatile variable should be visible to another thread after reading ready. Let's see what thread B does. Thread B reads D data into variable D and then it reads ready. And after reading ready, it is using D. Here we can't provide the guarantee of D to be 42 because the visibility of data is guaranteed to be 42 after it reads ready, not before it. So, volatile variables act like a visibility gate. Everything that is written before the volatile variable or performed before the volatile variable is visible to other threads after reading the volatile variable. So now let's look at another example where we have two volatile variables and a normal variable v. Thread A is setting all of them to 1 by setting x is equal to 1 after y and v. Now it is assumed that when thread B reads x as 1, y and v will be 1 as well. But the assumption only holds good for v, which is a normal variable, but not for y, which is a volatile variable. That is because each volatile variable has its own visibility gate. So only the actions performed on non-volatile variables before a volatile write are visible to another thread after the volatile read. So v, the value of b is equal to 1 is visible over here, but not y because it is a volatile variable. That brings us to the proper usage of volatile variables. They can be used as flags to indicate some action has taken place. Second, they can be used as independent variables that represents their own state, and they don't participate with other volatile variables to represent some invariant. As we have already seen, two volatile variables are not linked to each other and they don't necessarily provide fresh values with respect to one another. Third, if the code seems complicated after use of volatile variables, discard it and use locks. Fourth, variables should not perform any compound action, that is counter plus plus. As we have already seen, volatile variables provide us with visibility and a guarantee to no reordering, but they don't provide us with locking. So I++ example will fail with respect to volatile variables. One more point. Class report system can be made thread safe by converting report ready variable to volatile. After report ready is written to true, it is guaranteed that report ID is 101. And after report ready is read from thread 2, it is guaranteed that report ID will print 101 over here too. So report ready can act as a flag which is volatile. Now let's move on to the third concept, that is thread confinement. I've been a software engineer for a few years now, and I've written some code in my office work that is not necessarily thread safe. This code goes into an app which is used by multiple users. These users send multiple requests to the app at the same time. So how does my code work? So that is because framework assigns a single thread for each request and my code stays confined to that thread. So even though all the threads use the same code, each thread gets its own stack and local variables. So that's what makes the usage of my code thread safe even though the objects aren't. That is what is called thread confinement. Object confined to a single thread. Use becomes thread safe even though object isn't. So this confinement is not regulated by the JVM or compiler. It is the dev's responsibility and it is by program design or framework design. Now let's see what is ad hoc thread confinement. Thread confinement, which is done by program design, is called ad hoc thread confinement. It is not regulated by JVM or the compiler. It is simple, maintainable, but fragile. It is extensively used in enterprise applications. Now, why is it used extensively in enterprise applications even though it is fragile? Because the benefits outweigh the cons. Not every developer has in-depth knowledge about concurrency or the JVM memory model. Still, we write code every day which seems to work without any concurrency bugs in it. That is what makes it simple and maintainable. But one static variable can change everything. So unless and until you introduce a thread pool by yourself in the code, your code remains mostly single-threaded. Let's move on to the next type of confinement, that is stack confinement. Local variables within methods are stack confined. They are present in executing thread stack. So they aren't shared between the threads. Each thread gets its own stack. Primitive variables cannot escape this stack. Even if you try, they can't escape. But object references can. How can they escape? You can return them, you can store them somewhere, and then they can be reused by other threads. So stack confinement can also be violated by object references. Next type of confinement is done by thread local variables. Thread local is a class in Java and it gives each thread its own private value behind a shared variable. So the variable is shared by multiple threads, but each thread gets its own value. Get returns the most recent value written by the executing thread using set. So when we have shared mutable variables, we have two choices. Make it thread safe by using locks for synchronization, or make it thread confined by using thread local. Thread local provides ad hoc type of thread confinement. That is because values can be fetched from it, they can be stored and misused by other threads. So it is not regulated by JVM but by programmer's discipline. Now let's go on to its uses. It is effective when threads are reused, like in thread pools, to avoid repeated allocation of temp objects. Now if I have a thread and I need to allocate an object to it again and again, so what can I do? I can make use of the thread local variable, store the value in the thread, and whenever the thread is reused, just fetch the value from the thread instead of allocating it again and again. There is a warning though, that can cause memory leaks if not used properly. Thread local is also used to pass execution context and DB connection to methods which use @transactional for transactions in Spring Framework. So it is like a hidden argument to methods. You don't need to pass connection and execution context to methods explicitly. The framework does that for you. And how does it do that? By using thread local variables that map these both to the thread executing your request. So that's it for this week. We'll meet next week hopefully, and let's see what we cover in that. Till then, study and have a great time.